Hello everyone, welcome back to the channel. This is a third video in three-phase AC circuit series. In the very first video, I had gave you the introduction about the three-phase star and delta connection, and in the second video, we have derived the relationship between line and phase quantities in case of star and delta connection. If you haven't checked that videos, you can check that. The link is provided in the description box. In this video, I am going to discuss how to solve the problems in case of three phase systems, what is the active reactive and apparent power relationships in case of star and delta, what is the relationship between star and delta connected impedances, and ultimately we are going to compare star and delta connection. So let's start with the procedure which needs to be followed for solving three phase problems. Now, before discussing this, we need to know that the rating of three phase system is always in terms of line quantities. Now, what we mean by this, if it is given that we have a 400-volt supply system, 400-volt star connected supply system or delta connected supply system, it's not mentioned that which voltage is this. By default, it means that is line voltage. And if it is like a three phase star connected system has a phase voltage of 400 volt, then we have to take that as phase voltage. Otherwise, if it is not mentioned, then we have to take that as line voltage. Similarly, same applies to the current as well. If the problem states that the current through drawn by three phase load is 10 ampere, so that 10 ampere is for line current, not for the phase current. If it is that phase current, that has to be mentioned. So by default, the quantities are line voltage and line current. So when we have to follow the procedure, if the question is we have to find out the phase current or anything we need to find out, firstly line current and phase current are given, or the impedances are given in per phase values. ZP is per phase impedance. So our first step is calculate the phase voltage. First step is calculate Vp. Now Vp is equals to VL by root 3 in case of star connection, and Vp is equals to VL in case of delta connection. Then second step is calculate IP. IP is always phase voltage upon phase impedance. Now depending upon which connection is this, you can calculate the phase current. And after that, whatever is asked, if they you are asked to calculate power, which includes active, reactive or apparent, you can calculate them. And if the question is we have to find out the line current, we can say this one is going to be the fourth step. Let's first say the third step is calculate line current. Now in case of star connection, line current and phase current, they are same, while in case of delta connection, IL is equals to root 3 times IP. After that, you can calculate active reactive power, whatever required. But we can't calculate the line current. If the question is like the line voltage is given, phase impedance is given, we can't directly calculate the line current. We always need to calculate first the phase current, and for that we need the phase voltage. So we need to apply the relationships depending upon the connection. Now let's move on to the power in three-phase circuits. Now in three-phase circuits, we are considering the balanced system. Balanced means when all the voltages are same, all the currents are same, the per phase impedances for the three phases are same. So in balanced system, the three-phase power is equals to 3 times per phase power. So we can simply write P is equal to 3 times. Now per phase power is phase voltage into phase current into cos phi. Cos phi is the power factor of the circuit and phi is the angle between Vp and Ip. Similarly, reactive power 3 times Vp Ip sin phi, and apparent power is 3 times Vp Ip. So again they are 3 times per phase power. Now this power can be expressed in terms of line quantities. So irrespective of star connection or delta connection, this is the expression for power. Now line quantities, they have different relationship in star and in delta. So let's write for star first. In star connection, VL is equals to root 3 times Vp, or Vp is equals to root 3 times, sorry, VL by root 3. VL by root 3. IL and IP both are same. So P, which is equal to 3 times Vp Ip cos phi, that can be expressed in terms of line quantities. Vp is replaced by VL by root 3. IL is replaced by Ip cos phi as it is. So expression for power is root 3 times VL IL cos phi. Similar we can do for the reactive power as well as for the apparent power by substituting the value of Vp and Ip. So reactive power is root 3 times VL IL sin phi, and apparent power is root 3 times VL IL. Now if we do same changes in case of delta, in case of delta, line voltage and phase voltage, they are same. Line current is root 3 times phase current, or Ip is IL by root 3. Active power is 3 times Vp Ip cos phi. 3 times Vp is same as VL, Ip is IL by root 3 cos phi. So P is root 3 VL IL cos phi. Similarly, reactive power is root 3 times VL IL sin phi, and apparent power is root 3 times VL IL. So irrespective of the circuit, the relations for the active, reactive and the apparent power, they are same in terms of line quantities as well as in terms of phase quantities. So depending upon how the values are available with us, we can calculate the power with either this formula or this formula. Now we can find out the relationship between power in delta and star connected systems. Now let's consider that we have same load ZP which is connected in both star as well as in delta connection. ZP is same, the supply system is also same. Line voltage is same for both the systems. So when we have star connected load, ZP and VL are same for both star and delta connected system. So I am considering first case when the load is connected in star. So when load is connected in star, we need to calculate the power consumed by that load. So power expression is root 3 times VL IL cos phi. Line voltage is known to us, we need to calculate line current. For that, firstly we need to calculate phase current. So IP is Vp upon Zp. And in case of star connection, Vp is VL by root 3 on Zp. So when we use this value of IP for finding the current IL, so IL is equal to IP, it is VL by root 3 Zp. Now let's use this value of IL in expression of power. So in order to differentiate between power in star and delta, I am denoting it by Py. So root 3 times VL into IL. IL has value VL by root 3 Zp cos phi. So it's VL square upon Zp cos phi. So power in star. Now if the same load is now connected in delta, line voltage is remaining same, Zp and VL they are same as their value when they were connected when the load was connected in star. Now in case of delta connected system, Vp and VL both are same. We need to calculate IL which is root 3 times IP. For that we need the calculation of IP. IP is Vp upon Zp. Vp is same as VL, so VL upon Zp, and hence IL is root 3 times VL by Zp. Now substitute this value in the expression of power. So power in delta which is root 3 times VL IL cos phi. So root 3 VL IL is root 3 VL by Zp cos phi. So this is 3 times VL square Zp cos phi. So what we see in case of star connection, power was VL square upon Zp cos phi, while in case of delta, the same load which is now connected in delta across the same supply, it's 3 times the power consumed in case of star connection. So power consumed in delta is 3 times the power consumed in case of star connection. We can even find the relationship between the impedances, or we can say we can have the conversion of balanced star to balanced delta, balanced star to delta, or delta to star conversion. Means if a load is connected in star, that can be converted into delta. Now how that can be done? For a balanced load, if the line voltage is VL, IL is the line current, and phase impedance In case of star is denoted by ZY, and in case of delta it is connected by Z delta. Now in case of star, let's calculate the value of ZY. ZY is actually Vp upon Ip. Vp is equals to VL by root 3. Ip and IL, they are same. So Z star is VL by IL 1 by root 3. Now this one is for star and for delta. Let's say impedance is Z delta. Again it's Vp upon Ip. In case of delta connection, Vp and VL, they are same. Ip is IL by root 3. So Z delta is actually root 3 times VL upon IL. Now if we compare them or take their ratio, so what we have, Z star is equals to 1 by 3 Z delta. So if we need to change the impedance which was connected in star to delta, then ZD is equals to 3 times, sorry not Z delta is equals to 3 times ZY, that is the impedance in star. Now we can have the comparison of star and delta system. In case of star connection, VL is equals to root 3 times Vp. In case of delta, VL is equals to Vp. In case of star connection, IL and IP, they are same. But in case of delta, IL is equals to root 3 times Vp. In case of star connection, VL leads Vp by 30 degree, while in case of delta connection, IL lags behind IP by 30 degree. We have the power relation as well. So power in case of star is 1 by 3 of power in case of delta, or we can say for delta, P delta is 3 times the power consumed in the star. So in case of star connected system, we can have 3 phase, 3 wire system, or 3 phase. We can have 3 phase, 3 wire system, and or we can have 3 phase, 4 wire system. While in case of delta, we have only 3 phase, 3 wire system. Now what we mean by 3 phase, 4 wire system? In case of star connection, the connection is like this: 1, 2, 3. These are the 3 lines, R, Y, V. And then we have neutral. So if we connect another wire from here, then we have 1, 2, 3, 4. 4 different wires. So this type 3 phase 4 wire system is the most commonly used at the domestic level, because at domestic level most of the loads are single phase loads, and we need to use one line and second one is neutral, and that will act as a return path. So we can connect a single phase load like this, second single phase load like this, and third single phase load like this. While this type neutral is not available in case of delta, so delta is not useful for the domestic level distribution. So with this, I am ending the video over here. In the next video, I will be solving the numerical problems of the three phase. If you find the content on this channel useful to you, please consider subscribing the channel. Thank you for watching this video.